Good afternoon. In this tutorial, we're going to talk about on how much to be pre-designed reinforcement concrete buildings. But first, we're going to review the basic steps to design reinforcement concrete buildings. The reinforcement concrete buildings has 6 basic steps, which are: gather the basic information, the planning and structural system definition, applicable standards, the pre-design, which is the part that we are going to talk about in this tutorial, the structural design, and finally the drawing and specifications. On the first point, gather the basic information. The information that needs to be gathered is the soil analysis, sanitary facilities data, electrical data, and mechanical data. The soil analysis will give us the soil type and classification, the bearing capacity of the soil, the water table depth, the internal friction angle of the soil, and the weight of the soil. Also, this information will help us to choose the proper type of foundation to use, and is an important data for seismic analysis. Sanitary facilities data will recollect the possible sanitary connection point with the main clean water pipeline system and the main sewer pipeline system. The electrical data will give us the possible points of connection with an existing power line or if a transformer is required. The mechanical data will give us the dimension of elevators or special equipment that will help with the disposition of the column or shear walls. Second point, planning and structural system definition. Well, it's hard to establish a general rule to select a structural system and their elements. You need a good base of knowledge on different types of structure and how they can behave in normal situations and under dynamic forces. And sometimes you need a little imagination to adapt it to a specific problem. But in general terms, to start any project, the first things to do is meet with an architectural professional to review the conceptual design and get in agreement about structural materials, height of the building, height of each story, and the preliminary disposition of column, beam, or shear walls. Talking about the location of column, beams, or shear walls, this is one of the most important factors. We define the structural system and structural cost of the project. Column location will define the span of the slabs and beams. Slab span will define the type of slab to use that will affect the weight and the cost of the structure. The third point, applicable standards. It's important to have this point pretty clear. It's a good practice to meet with the local authorities to define which will be the standards to use in the project. Sometimes there are owners or authorities that has their own specification based on national standards, and they rather use them than the national ones. The fourth point, the pre-design. When we have already defined the structural system to use, we should do a preliminary sizing of the elements to see how will influence on the different environments of the building. Also, have a likely knowledge of the cost and the building stiffness. The fifth point, structural design. After has defined a structural solution that satisfies the architectural and economic requirements, we proceed to analyze the structure with more precise methods as finite elements software and define the reinforcement required. The sixth point, drawing and specification. With the structural design already checked with the standards, we proceed to do the blueprints of the building, detailing the amount of the reinforcement, the strength of the concrete, and the final dimension of the elements. Also, we create the specification of the project as design criteria, engineering report, measurement and payment, and metric calculations. After review, the basic steps to design reinforcement concrete buildings. Now we are going deeply into the steps to pre-design reinforcement concrete buildings. The pre-design of Reinforcement concrete buildings are divided in these 5 steps: structural system selection, slab system selection, pre-design of the columns, pre-design of load-bearing beams, and pre-design of anti-seismic beams. As commented before, the first step is to select the proper system for our design. For to this, we are going to understand the different types of systems that exist. The buildings are classified into types: to resist vertical force and to resist lateral force. The vertical force resistance system is subdivided into types: with interior beam system and without interior beam system. The system with interior beams is composed by slab, which has 2 basic types: beam slab and rivet slab, and can be designed in 1 or 2-way directions. The other components of this system are beams, columns, shear walls, and foundations. The other system, without interior beams, is composed by the slab, which could be flat slab or wafer slab, and only can be designed in 2-way directions. The other elements of this system is columns, shear walls, and foundations. The lateral force resistance systems. When the project was planned, the height of the building was settled. With this information, we can select the proper system to use to resist the lateral force due to the wind and the seismic loads. We can organize them in these 4 basic types of systems, depending on the height of the building to be designed: reinforced concrete moment-resistant frames, shear wall systems, dual systems, and the tube-in-tube structural systems. The maximum height recommended for these buildings are: for reinforced concrete moment-resistant frames, 15 stories; shear wall system, 35 stories; for dual systems, 45 stories; and the tube-in-tube structural system, 90 stories. These maximum height recommended are based on the experience of the project cost and architectural requirements. The reinforcement concrete moment-resistant frame is the most common type of the system used in structural design, and is composed by beams, columns, brace frame, slabs, and foundation. The shear wall system is composed by slabs, shear walls, and foundation. The dual system is composed by beams, columns, brace frame, shear wall, slabs, and foundation, and the tube-in-tube structural system is composed by shear wall or columns near between each other as a core in the center of the building, and outside ring composed by beam, columns, brace frames, shear walls, and foundation. Also, can be taller if include an outrigger belt. Slab selection system. After having defined the structural system and the disposition of the column or shear walls, we can select the proper slab system for the structure in accordance with the span between columns or shear walls as mentioned before. There are 4 basic slab systems depending on which type of structural system was chosen. It was system with interior beams or system without interior beams, in agreement with architecture professional and attending the architectural requirements. The recommended type of slabs to use, according with the span between columns or shear wall, is for the system with interior beams, 1-way direction beam slab for a span from 1 to 5 meters, 2-way direction beam slab for spans from 5 to 8 meters, 1-way direction rivet slab for spans from 3 to 7 meters, and 2-way direction rivet slab for a span from 7 to 10 meters. And from the system without interior beams, 2-way directional flat slab for a span from 1 to 8 meters, and 2-way direction waffle slab for a span from 5 to 15 meters. If the position or span between columns is greater than 50 meters, it's recommended to use a pre-stressed slab. After having selected the slab system to use according with the columns or shear wall spans, we shall calculate the thickness of the slab in accordance with the American Concrete Institute 318 standard. If the system selected was with the interior beams, we shall use the table 7.3.1.1 for one-way direction slab as described herein. We have to see which type of support condition has our slab system. If it is simply supported, one end continuous, both end continuous, or cantilever. The simple supported condition refers for panels that not has continuity in each of its ends. Is the typical frame system composed by 4 columns, 4 edge beams, and the slab. The one-way continuous condition is the panel that has one end continuous in one or two orthogonal directions. For example, this panel matches with this condition. In the X direction has continuity with the right panel, and in the Y direction has continuity with the upper panel. The both ends continuous condition is the panel that has both ends continuous in one or two orthogonal directions. For example, this panel complies with this condition. In the X direction has both ends continuity with the left and the right panel adjacent, and in the Y direction has continuity with the upper and the bottom panel adjacent. The cantilever condition is the panel that extends horizontally outside the system but belongs to the system and is supported at only one end. For example, a balcony in a building. The thickness of the two-way direction slab is calculated with the table 8.3.1.1 based on these equations, where the conditional factor is the average of the beam slab stiffness ratio. To calculate this factor, we have to know the thickness of the slab and the dimension of the beams. At this point, these are variables that we don't know yet. To solve this problem, we do a little transformation of the equation B by changing the average beam to slab stiffness minus 0.2 for 1 plus beta s, where Bs is the ratio of the continuous end span to the perimeter of the slab. We select the equation B because we are going to design a slab supported by beams with ability to develop a deflection or bending when a bending moment is applied. If we select the equation C, we are going to design a slab supported by a stiffness beam. It's important to notice the comment of the sections 8.3.1.2 of American Concrete Institute 380 standard. For panels having a region of long to short span greater than 2, the use of the expression B and D of the table 8.3.1.2, which give the minimum thickness as a fraction of the long span, may give unreasonable results. For such panels, the rules applying to one-way construction in 7.3.1 shall be used. The thickness of the slab for system without interior beams is calculated with the table 8.3.1.1 American Concrete Institute 380 standard. We need to select the proper system attending to architectural requirement if it is with or without door panels. After that, we shall define if it will have edge beams or will be without edge beams. The pre-design of the slab thickness explained so far is for solid slabs. To calculate the thickness of river slabs for system with interior beams or waffle slab for system without interior beams, we shall do it through equivalent sections and calculate the inertia of both shapes. We are going to increase or decrease the height of the sections of the river or waffle system until the value of the inertia is equal or greater than the equivalent section. Loads. After having defined the slab thickness, we can determine the loads that will be transmitted from the slab to the beam, shear walls, and columns. There are three basic types of loads: dead loads, live loads, and environment loads. In the pre-design, We just work with the dead loads and live loads for columns and building load beams, and seismic loads for anti-seismic beams and shear walls. Dead load definition. The dead loads are all those loads that belong to the structure, such weight of the concrete and the weight of the all materials of construction that will be incorporated into the building as leveling codes, type of floor, or waterproof roof. To calculate a specific weight of construction material, it is recommended to look in the vendor catalog. There are several generic tables and pages that you can use in obtaining of the definitive information that have to be approved by the authority before using them. The basic dead loads that should be included in the design, but not limited to, are for roof slabs, self-weight, leveling coat, waterproofing, and freezes. For a structural floor, self-weight, leveling coat, flooring loads, depending on the architectural requirement, could be tile, timber, vinyl, etc. On the walls, the perimeter walls, and the internal division. Live load definition. Live loads are those that we produce by the use and occupancy of the building, person or equipment that doesn't include construction or environmental loads, and shall be determined by the Table 4.3.1 of the American Society of Civil Engineers in accordance with the occupancy or use. For design of the columns, with dead loads and live loads defined, we proceed to calculate the cross-section area of the columns using this formula, where P is the axial load transmitted from slabs to the column through a distributed area for each column. Alpha is a factor that depends on the location of the column, and its value is 0.28 for central column, 0.25 for border columns, and 0.2 for corner columns. And finally, FC is the composite strength of the concrete that shall be 3,000 pounds square inch as minimum, as required on Table 19.2.1.1 of American Concrete Institute 318 standard for seismic buildings. To calculate the axial force transmitted from the slabs to the columns, we'll do it through a tributary area defined as the half distance of the cure span in each orthogonal direction of the columns to be analyzed. The axial load that will be applied to the columns is calculated with this formula, where L and B are the half distance of the cure span, which will define the area of the column that will be analyzed. WC is the total weight per square inch of the slab, and N is the number of histories that have the same time of a slab. For example, we are going to pre-design this column, assuming a building of 4 stories for residential use, composed by 1 roof slab and 3 structural floors with a slab thickness of 8 inches. The first thing that we are going to do is calculate the tributary area that affects the column. The panel has these dimensions: in X direction 195 inches, and in Y direction 235 inches. The half distance is for X direction 97.5 inches and for Y direction 170.5 inches. Now we are going to calculate the total weight of the roof slab and structural floor based on the constructive materials that are composed. After have defined the tributary area that affect the column, we are going to calculate the dead and live loads for roof slab and structural slab as follows, starting with dead loads. For the roof slab, the self-weight is the specific weight of normal concrete multiplied by the thickness of the slab. The leveling coat is the specific weight of the lightweight concrete multiplied by assumed thickness of 2 inches. The waterproofing weight was obtained from vendor catalog. The freezes is the code that will give the slope for a rainwater runoff. The total weight of the roof slab is 0.916 pounds square inch. The axial load transmitted from roof slab to the columns is 10,495 pounds. For the structural floor, the self-weight is the specific weight of the normal concrete multiplied by the thickness of the slab. The leveling coat is the specific weight of the lightweight concrete multiplied by assuming thick of 2 inches. The flooring load was selected tiles, which has a specific weight of 0.03 pounds square inch according to the Super Catalog. The walls, composed by clay bricks and friezes with a specific weight of 0.26 pounds square inch. The total weight of the structural floor is 1.154 pounds square inch. The axial load transmitted from the structural floor to the columns is 13,320.5 pounds. Live load. According with American Society of Civil Engineers, Table 4.3.1, minimum uniformly distributed live load for an ordinary flat roof, the uniform load is 0.139 pounds square inch, and for residential use is 0.278 pounds square inch. With the dead and live loads defined, we're going to use the basic load combination from Table 5.3.1 of the American Concrete Institute 318 standard to calculate the factory load that we are going to use to define the preliminary cross-section area of the column, resulting in a final axial load transmission of 60,190.13 pounds. The preliminary cross-section area of the column is 100.32 pounds. The American Concrete Institute 380, Section 18.7.2.1, defined for a special moment frame system dimension limits for columns, and established that the shortest cross-section dimension of a column should be at least 12 inches, which means the minimum gross area for a column is 144 square inch. Our column doesn't match this requirement. The gross section for our column will be 144 square inch. Redesign of load-bearing beams. With the dimension of the columns already calculated, in our case 12 inch each orthogonal direction, we proceed to calculate the load-bearing beams by calculating the load per unit area according with the load combination from American Concrete Institute 380 standard. The result will be multiplied by the hard distance of the orthogonal direction of the beam span to obtain W, which is the factory load per unit length. After that, we calculate the theoretical moment of the beam, which always for frames, all elements are considered fixed in both ends. With the theoretical moment calculated, we proceed to calculate D, which is the distance from a string compression fiber to the centroid of longitudinal tension reinforcement of the beam, where B is the width of the beam, Phi is the stress reduction factor, and Ru is a value based on ratio reinforcement and the strength of the concrete to guarantee the ductility of the beam. The final preliminary height of the beam is the sum of D plus C, where C is the cover distance. Finally, we perform the contour deflection based on the table 9.3.1.1 of American Concrete Institute 380 standard. Now, we are going to redesign this beam on the roof slab, knowing that the width of the beam is 12 inches. The dead and live loads were calculated in the previous step, pre-design of columns, where the dead load is 0.960 pounds square inch and the live load is 0.139 pounds square inch. Using the load combination equation, 1.2 dead load plus 1.6 live load, the result is 1.322 pounds square inch. The half distance of the orthogonal direction of the beam span is 97.5 inch. Factory load per unit leg W is 128.9 pounds per inch. Now we calculate the theoretical moment with this equation, resulting in 539,208.54 pound-inch. The depth of the beam is 11.24 and we approximate it to 12 inch. The height of the beam is 14 inches. Now, using the table 9.3.1.1 of American Concrete Institute 380 standard, we verify that the height of the beam is inside the maximum height allowed by the standard. This beam has one end continuous and the applicable condition is 18.5. We make the verification and the height of the beam is inside the parameters. After has pre-designed the columns, load-bearing beams, and slab of the structure, we are ready to calculate the total seismic weight and the seismic response coefficients to calculate the seismic base shear as requested on American Society Civil Engineering Standard, and do the distribution of the lateral forces for each history. With these lateral forces, we will use an equation derived from the rotational method, solving Kv from the equation, where delta is the relative displacement that will be calculated according with the table 12.12.1 of American Society of Civil Engineers. T is the lateral force of the history that is being analyzed. H is the height of the history. ED is the dynamic modulus of the concrete. Kc is the stiffness of the column, and Kd is the stiffness of the beam. Ki is the distribution of the beam stiffness between frames of the analyzed level. Kb is the beam stiffness of each beam from the determined frame. Lb is the inertia of the beam, and Hb is the height of the beam. For example, we are going to pre-design this anti-seismic beam from the roof slab with a length of 161.42 inches. Because it's for residential use, the risk categories for this building is 3, and from soil analysis, the seismic design category is D. According with table 12.12.1, the allowable story drift limit is 0.02 multiplied by the history height from the base, and the seismic design category D is divided by redundancy factor equal to 1.3, as requested on section 12.3.4.2 of American Society Civil Engineers Standard. The allowable story drift for the roof is 7.3 inches. After has calculated the allowable story drift for the roof, we calculate the inertia of the columns to calculate their thickness, given 14.4 cubic inches as result. Due the structure has 12 columns, the total column stiffness for the roof history is 172.8 cubic inches. Applying the equation derived from rotation method and knowing the lateral force for the roof is 22,000 pounds and the dynamic modulus of elasticity of the concrete for a strength of 3,000 pounds per inch, we proceed to calculate the total beam stiffness required for anti-seismic beams, with a value of 14.14 cubic inches. After have calculated the total beam stiffness required to satisfy the allowable story drift displacement, we proceed to distribute it to the beams. The first thing to do is distribute the total beam stiffness to the frames of the history. In our case, are 3 frames in the history, giving a result of 4.71 cubic inches. The second step is distributed between the beams that belong to the frame. In our case, there are 3 beams in the frame. Using the equation for calculate Kb, where n is the number of the beam that belongs to the frame, Lb is the clear span of the beam that has been calculated, and L is the total length of the frame, giving a result of 1.23 cubic inches. The third step is calculate the inertia of the beam, resulting in 198.55 double square inch. And finally, we calculate the height of the beam, solving H from inertia equation, giving a result of 5.83 inches that we approximated to 6 inches. The finally preliminary dimension of the element of the structure are columns 12 by 12 inches, load-bearing beams 12 by 14 inches, and anti-seismic beam 12 by 6 inches. This concludes this tutorial.